I will compare two ion coordination complexes, namely hexa-aqua-ion 2 ion and hexa-cyanidoferrate 2 ion. Both complexes contain the same central metal ion, which is Fe2+, and both has 6 ligands surrounding the metal center. Therefore, both complexes have a coordination number of 6 and adopt an octahedral geometry. However, the ligands are different. Water is a weak field ligand, whereas cyanide is a strong field ligand. The differences in ligand strength causes significant differences in their electronic structure, magnetic properties, and color. Next, we determine the oxidation state of ion in each complex. For hexa-aqua-ion 2 ion, water is a neutral ligand with zero charge. Therefore, the oxidation state of ion must be +2 to account for the overall +2 charge. For hexa-cyanidoferrate 2 ion, each cyanide ligand carries a charge of -1. Since there are 6 cyanide ligands, the total ligand charge is -6. To obtain the overall charge of -4, ion must have an oxidation state of +2. Hence, ion exists as Fe2+ in both complexes. To determine the d-electron count, we must write the electronic configuration of neutral ion first. Ion has atomic number of 26, giving the configuration 3d6 4s2. When ion form Fe2+, 2 electrons are removed from 4s orbital, resulting in 3d6. Therefore, Fe2+ contains 6d electrons. Since both complexes contain Fe2+, both complexes are classified as D6 system. The coordination number is the number of donor atom directly attached to the metal center. In both complexes, 6 ligands are bonded to Fe2+. Therefore, both complexes have a coordination number of 6. A coordination number of 6 generally results in a octahedral geometry where the 6 ligands are arranged symmetrically around the metal ion. For the type of ligand, the ligand in these complexes differ significantly in their field strength. Water is a neutral ligand and acts mainly as a sigma donor. It is classified as a weak field ligand and therefore produces a small crystal field splitting energy. Cyanide is a negatively charged ligand. It is a strong sigma donor and also a pi acceptor ligand. As a result, it produces a much larger crystal field splitting energy value. According to the spectrochemical series, cyanide is much stronger than water, which explains why these two complexes exhibit different electronic and magnetic properties.
Next, I will explain the crystal field theory for the first complex, which is hexa-aqua-ion 2 ion. The central metal ion is Fe2+, which has the electronic configuration argon 3d6. In an octahedral complex, the 5d orbital will split into two energy levels, which is the lower energy T2g orbital and the higher energy EG orbital. The ligand in this complex is water. H2O is a weak field ligand because it is located low in a spectrochemical series. It does not repel the metal d electron strongly, resulting in small splitting energy. Since the energy gap between the T2g and EG orbital is small, it requires less energy for electron to occupy the higher energy level than pairing up in the lower energy T2g orbital. Therefore, according to the Hans rule, the electron will fill up the orbital singly before the pairing up occurs. As a result, the 6d electrons are arranged as T2G4, EG2, giving 4 ampere of electron. This make the hexa-aqua-ion 2 ion a high-spin complex and therefore strongly paramagnetic. Finally, because the crystal field splitting energy is small, it means that the electron require lower energy to jump to the higher energy level. Lower energy correspond to a longer wavelength of light, such as red or orange. As a result, the complex reflects the complementary colors blue-green, which is the why the solution appears pale green.
From the crystal field theory, for ferrocyanide, the metal center is ion 2+, and the ligand is Cn-, where it's strong field ligand. For the ion neutral, the electron configuration is 4s2, 3d6. For the ion 2+, the two electron removed at the 4s become 3d6. From this field ligand, we can see the ground state of ion neutral has in a low energy, while we remove the 2 electron in 4s, we can see the 3d orbital has a bit higher energy. After splitting, we can see the electron field up in a T2G, while EG has no electron due to the strong field ligand, and it's become a large splitting energy. And also, we can see it in low spin, and the magnetic properties is diamagnetic. And from that, we can observe the color, where the absorption of highest energy in visible light, the absorption is in blue violet region, and the appearance that we can see is pale yellow. Also, from the calculation CFSE, we can see the -2.4 delta of plus 3p. 3p is considered a 3 electron pair, which is in T2G we can see 3 electron pair in this region.
Now, let's look into the molecular orbital theory of hexa-aqua iron 2 ion. This is Fe2+, D6 octahedral surrounded by 6 water molecules. Sigma bonding. Each water donates a lone pair. The 6 lone pairs combine by symmetry into A1G, T1U, and Eg, matching the metals 4s, 4p, and Eg orbitals. This gives a low field bonding set and a high anti-bonding set, Eg. The metals T2G orbitals dxy, dxc, and dyz sit out of this. They point between ligands and not at them. Pi bonding. Water also has filled lone pairs of pi symmetry on oxygen, sitting in lower in energy than the metal d orbitals. This makes water a pi donor. These interact with the metal T2G set, and since they are filled and low, the metal-based antibonding combination T2G and the antibonding gets pushed up. For the effect of the energy difference and filling, pushing T2G the antibonding up shrinks the gap to Eg antibonding. The energy difference is small, with 6d electrons, and a small gap, it's cheaper to spread them out than to pair up. T2G and Eg of antibonding, 4 unpaired electrons, high spin and paramagnetic. So, hexa-aqua iron 2 ion is a high spin because water is a weak field pi donor that raises the metal's T2G level and keeps the energy difference small. This is the MOT diagram for the hexa-aqua iron 2 ion. Followed by, let's look into the molecular orbital theory of hexacyanatoferrate 2 ion. It's the same metal, Fe2+, D6 octahedral, now surrounded by 6 cyanide ions. Sigma bonding. Each cyanide ion donates a lone pair from carbon. The 6 combines into A1G plus T1U plus Eg, matching the metals 4s, 4p, and Eg orbitals. Same as before, field bonding set low, anti-bonding, Eg high. T2G again sits outside this sigma system. Now for pi bonding, cyanide is different from water here. It has high energy pi antibonding orbitals on the cyanide triple bond of T2G symmetry. This makes cyanide ion a pi acceptor. This interact with the metal's filled T2G set, and since the ligand orbital is empty and high in energy, the metal-based bonding combination T2G gets pulled down. Effect on the energy difference and filling. Pulling T2G down widens the gap to Eg antibonding. The energy difference is large. Now pairing electrons causes less energy than promoting them across that big gap, so all the 6d electrons pack into the lower level, T2G 6, Eg antibonding, 0 unpaired electrons, low spin, diamagnetic. So this compound is low spin because cyanide is a strong field pi acceptor that lowers the metal's T2G level and opens up a large energy difference. This is the MOT diagram for the hexacyanatoferrate 2 ion.
I will present the comparison between the hexa-aqua iron 2 complex and the hexacyanatoferrate 2 complex. From both crystal field theory and molecular orbital theory, we can see that the two complexes have very different properties because they have different ligands. Water, H2O is a weak field ligand, so it produces a small crystal field splitting energy, or we can call it as delta delta. As a result, the electrons remain unpaired whenever possible, giving a high complex that is paramagnetic. On the other hand, cyanide is a strong field ligand. It produces a much larger delta delta, causing the electron to pair in the lower energy T2G orbitals. Therefore, the hexacyanatoferrate 2 complex is a low spin and diamagnetic complex. Overall, the stronger ligand field of cyanide results in a stronger metal-ligand bonding and different magnetic behavior compared to the H2O complex. In this slide, we will discuss why molecular orbital theory is better than crystal field theory. Although crystal field theory successfully predicts the splitting of the d orbital, it doesn't explain why different ligands produce different values of delta delta, while molecular orbital theory provides a deeper explanation by considering the overlap between metal and ligand orbitals. For the hexacyanatoferrate 2 complex, the cyanide ligands act as a strong pi acceptor. Through pi bonding, it accepts electron density from the ion, which lowers the energy of the T2G orbital and increases delta delta. This stronger orbital interaction also strengthens the ion and CN bond. In contrast, H2O mainly only acts as a sigma donor and doesn't have a significant pi acceptor effect. Therefore, the delta iota remains smaller, giving the rise to the high spin configuration.
To determine the oxidation state, we use the overall charge of the complex together with the charges of the ligand. For hexa-aqua ion to ion, water is a neutral ligand, so ion must have an oxidation state of +2 to produce the overall +2 charge. For hexacyanidopherate to ion, each cyanide ligand has a charge of -1. 6 cyanide ligand contribute a total charge of -6. Since the overall charge is -4, ion must again have an oxidation state of +2. After determining the oxidation state, we calculate the d electron count. Neutral ion has the electronic configuration of 3d6 for s2. Forming Fe2+, remove the 2 for s2 electron, giving 3d6. Therefore, both complexes contain Fe2+ and have a d6 electronic configuration.
Now we go for the question number 2. Based on the crystal field theory, how are the d electrons arranged in each complex? Based on the crystal field theory, both complexes contain the Fe2+ ion, which has a d6 electron configuration. However, the arrangement of the d electron is different because each ligand have a different strength. For the first complex is hexa-aqua ion 2 ion. Water is a weak field ligand, so it will produce a small splitting energy. Since the splitting energy is smaller than electron pairing energy, electron will occupy the higher energy level first, which is Eg orbital, before the pairing up occurs. Therefore, the 6d electrons are arranged as D2G4, Eg2, with 4 ampere electron. This makes the complex is a high spin complex and it is a paramagnetic. For the second complex is hexacyanopherate 2 ion. Cyanide is a strong field ligand, so it will produce a large splitting energy. Because the splitting energy is greater than the electron pairing energy, the electron will pairing up in the lower energy D2G first before they occupy the Eg orbital. As a result, the electron arrangement is D2G6 Eg0 with no ampere of electrons. This makes the complex is a low spin complex and it is a dimagnetic.
In question 3, which complex has large splitting energy and how it affects color, spin state, and magnetic behavior? As we can see, the large splitting energy is FeCN64-, while it will affect the color, which is, in color, is due to the large splitting energy, the absorb of high energy in ultraviolet or blue-violet light, and it appears a pale yellow, whereas the FeH2O62+ has a smaller splitting energy, but it absorbs the lower energy, and in red light it appears a pale green. For its spin state, we can see from the large splitting energy at FeCN64-, the force of energy is paired up in the lower energy level in making a low spin complex, while the smaller splitting energy at FeH2O62+ is a low electron to occupy high energy level, and it obtain the unpair and making it in a high spin complex. Also, the third is magnetic behavior, which is due to the low spin arrangement in FeCN64- has a 0 unpaired electron. We can call, and the magnetic behavior is dimagnetic, and which is not attracted to the magnetic. Whereas the FeH2O62+, we can see a 4 unpaired electron, making it paramagnetic, which is attract to magnets.
Now, for the fourth question, molecular orbital theory explains these complexes better than crystal field theory because it considers both the sigma and pi bonding. For hexa-aqua ion 2 ion, water is a weak sigma donor, giving a small energy difference and high spin complex. Meanwhile, for hexacyanidopherate 2 ion, cyanide is a strong sigma donor and pi acceptor. Pi backbonding increases the energy difference, producing a low spin complex. Therefore, MOT provides a more complete explanation of the bonding and electronic properties of both complexes. Over here we can see CFT, which is the crystal field theory, considers only electrostatic attraction between the metal ion and ligands. Also, it explains high spin versus low spin, but does not explain why ligands differ in field strength. But MOT, the molecular orbital theory, considers orbital overlap and covalent bonding. Not only that, it also explains sigma bonding and pi backbonding. It also shows that Cn-, the cyanide ion, is the pi acceptor, which increases the energy difference by stabilizing the metal ligand bond, whereas H2O is only a sigma donor.
So, based on both CFT and MOT analysis, the hexacyanophoric 2 complex has the stronger ligand field. CFT predicts that the larger delta iota leads to low spin and diamagnetic complex, while MOT explains that this larger delta iota arise because cyanide is a stronger pi-acceptor ligand that forms stronger orbital interaction with the ion. In comparison, the hexa-aqua ion complex has a smaller delta iota, remain high spin, and is aromatic and form relatively weaker metal ligand bonds. In conclusion, combining crystal field theory and molecular orbital theory allow us to understand not only the difference in delta iota, spin state, magnetic behavior, and bonding strength, but also the orbital interaction responsible for these properties.